All right, welcome to another lesson of college algebra through modeling. Today is Unit 7, Lesson 5, Logistic Functions, or as I like to call them, Logistic Functions, for obvious reasons. Today's goal, well, your goal might be to survive another one of Mr. Larson's lessons. Today's goal for people who are keeping score at home is to be able to use a given modeled logistic function to make predictions about the real world. Now, looking at what we've already learned, we've talked about exponential functions, which start out slow and start growing faster and faster as time goes on. We talked about bacteria, where the more bacteria that there are, there's more that can reproduce, so the reproduction becomes faster, faster, and faster. Or with Bitcoin recently, it was growing faster, 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 and faster, but there's always kind of a limit. With bacteria, eventually they run out of space or they run out of food, so it starts to level off. And with Bitcoin, it starts to level off, which means a couple of things. One, Mr. Larson isn't retiring anytime soon. And maybe just as important is we need a new function, which brings us to the logistic function. Notice the beginning of the logistic function looks kind of like an exponential function. It starts out slow and it speeds up. But then it starts to slow down and level off. So if you remember back to logarithmic functions, we have an exponential function which starts slow and gets faster and faster and faster. And we have a logarithmic function which starts fast, but then gets slower and slower and slower. So this logistic function is kind of what would happen if an exponential function and a logarithmic function fell in love, had a baby. The baby would be a logistic function. It starts out fast, but then due to what we're going to call a carrying capacity, right? Like the bacteria run out of room, they run out of food, the growth starts to slow down and it levels off at an equilibrium. All right, so if we're looking at kind of the pieces of a logistic function, we have our initial value, which you can see here can be found by the value c. This is our function over here, c divided by 1 plus the a. Now, the c stands for the carrying capacity. So when you look at the function, you immediately know by that top number what the carrying capacity is. Where's this value going to max out at? Then there's this point, as it's growing fast, at some point it starts to turn to growing slower and slower and slower. So you have a point of maximum growth. And you can find the x value, which remember that's time, by taking the natural log of the a value divided by b. And if you look over at the y value, which is the amount of at any given time, it's always the carrying capacity divided by 2. So that's kind of easy to remember. Whatever the max value is, half that is where the maximum growth is happening. So let's take a look at an example. Let's say a student is infected with a virus and comes to campus. The function below gives the number of students infected, y, after x number of days after the infected student arrived on campus. So looking at this function, the top value, remember, that's your carrying capacity. So I know where this is going to level off and kind of reach its maximum value is at 10,000 students. At that point, maybe that's how many kids are on campus, so you can't exceed that. Or maybe once you get to that value, there's so many kids who have been infected that getting another person infected is a very low probability. So I can answer that without doing any math. What's the carrying capacity? What's the max number of students who can be infected is 10,000. Now, do these next problems, like how many will be affected after 4 days? We're going to use Desmos to kind of break that down. Remember, our x value is time. So this 4 is our x value. So when they say 4 days, it's kind of like they gave us the x value. We're trying to find the y value. The next question, how many days will it take for the population that's infected to reach 5,000? So here they give you the number infected, and that's the y value. So for this problem, think of it as they gave you the y value. We need to figure out what's the x value at that. And then the last one, question that we're going to answer is, after how many days will the infection be spreading the fastest? And we'll talk about, there's kind of really 2 ways to kind of go about solving that. All right, so let's load up Desmos and plug in this particular function. And again, the first one I answer right off the bat, that's 10,000. And when you're entering this into the Desmos app, make sure you don't put a parentheses in the 10,000. It does not like parentheses, so you're just going to type 10000 divided by 1 plus 9,099 raised to the negative 0.99x. And here you can kind of see the start of the curve here. It looks exponential, like it's growing. And if we zoom out so we can see the whole thing where it's going to level off, oh, we see it levels off here. But they almost look like straight lines because the curve part on the x scale happens in such a quick time that when we zoom out, you can't really see it. So I'm going to adjust the x scale here so we can kind of see the curve better. X minimum, I'm going to put -1, and the x value, I'm going to put 40, and y value, I'll put -1, and the max value for the y, I already know it's the max is 10,000, so I'm just going to go a little bit above 10,000, do 10,500. So that kind of gives me a good view of our graph. All right, so how many will be affected after 4 days? Remember, 4 days, that's the x value. So all I need to type in is x equals 4, and then see where that crosses our function. So when x equals 4, the number is 52.189. We'll round to the nearest person, so that's 52. After 4 days, 52 students will be infected. Now let's do the next one. When will, in how many days will the population that's infected reach 5,000? And so I type in y equals 5,000, and that is 9.3. And if I round to the nearest day, 9 days. Now, I kind of wasn't really thinking when I picked that 5,000, because the next question is, after how many days will the infection be spreading the fastest? Well, we already know that happens when you reach half the carrying capacity, which is 5,000, which we've kind of already answered because I wanted to know when the population would be 5,000 in the previous question. So we get the 9.3 again, or if you round 9. So really, when will the population that's infected reach half the max is the same question as when will it be growing the fastest? All right, let's do one more example. All right, so we're going to do a thing on deer population. So let's say we put one pair of breeding deer onto an island, and they start to reproduce. And as we get more deer, they reproduce faster and faster. So it's going to start out almost like an exponential curve. But at some point on this island, the food is going to be limited. And the more deer there is, it's easier for people to other animals to prey on deer. They're easier to find, right? So it's going to level off at some point. And what's the carrying capacity? It's always that top number in the function, which is 180. So right now I know the carrying capacity. The most deer that can live on this island is 180. That's when the population is going to level off. So some other questions I want to know is how many deer will there be after 20 years? How many years will it take for the population to reach 150? So we know the max is 180. I want to know how many years will it get to for it to get to 150. And after how many years will the deer population be growing the fastest? All right. So again, we're going to type that function right into our Desmos. So we have y equals, and I see when I was doing this in Desmos, I never hit the home screen. So right now it's probably already going to look pretty decent with the graph without having to adjust any of my X scale or my Y scale to make it look good. I think I'll probably go back to my home screen so you can kind of watch me kind of fit the view again. All right, so yeah, as you see, it already looks great, but I'm gonna go back to the home. And so again, when you start at the home, it looks exponential because that's kind of the part of the graph that it's looking at. And if you zoom out, the X change happens so quickly that it only happens over a short period of X. And so it starts to look like a straight line if you zoom out too much. So we're going to change the scale. Again, X, I always do -1. And then the bigger X, I can kind of look and kind of see here's 50, right? And it was smaller than that, so I put 30. And again, try some different numbers out until you find one that works good. All right, so now let's answer these other questions. So I already know the carrying capacity is 180. How many deer will there be after 20 years? All right, so again, time, that's my x value. So I go x equals 20, and I see where it crosses my function. It's at 179 point something. So that's basically 180. Because as you can see, it's already gotten to basically the max value by 20 years. So it's kind of already hit that 180 mark. And anything more than 20 years, you're going to get pretty much an answer that's 180 if you go past 20 years. All right, so now we're going to see, when is the population going to be 150? That's the y value. So y equals 150. Where does it cross the function? We get 10.9. So if I round, that's after 11 years it will take for this deer population to get to 150. And lastly, how many years will it take for the deer population to be growing the fastest? And so there I'm going to use this function that we learned. So natural log of 89, which is this value right there in the function, over this value, the positive 0.5554, and that gives it to you. The other way to do it is, I see the max is 180, so I go to half that, 90. Y equals 90, and if you put that function in there, it would also tell you the correct value, because again, it's growing the fastest at half the value of the max, and the max was 180, so I know it'll be growing its fastest when y equals 90. Or you can use that natural log function. And that concludes this lesson. So you'll be given a logistic function that models a real-world situation, and you'll have to make some predictions using that function and using Desmos.